Have you ever found yourself just staring at a new machine learning problem, maybe? Or, this overwhelming stack of technical papers, and just wish you could instantly find those key insights, those aha moments, without getting totally lost in the weeds?
Oh, absolutely. It's a really common challenge, isn't it? We get bombarded with information,
Yeah.
and the real skill isn't just collecting it all, but really understanding it
Yeah.
and making it actionable. That's the hard part.
That is exactly what we're diving into today, the fascinating world of machine learning, but focusing specifically on how we work with structured data.
Right.
Spreadsheets, databases, transaction records, data that's already kind of neatly organized in rows and columns. It's really the backbone of so much data science work out there.
Yeah, it really is. And our guide for this deep dive is Matt Harrison's fantastic book, Machine Learning Pocket Reference, Working with Structured Data in Python. It's incredibly practical, very comprehensive. And our mission today is basically to give you a powerful shortcut. We've pulled out the critical bits, the surprising facts, those essential insights. The goal is you can quickly get up to speed, feel informed, and be ready to tackle real-world problems, building effective predictive models.
So we're going to walk through that whole core process then, from really understanding the data, prepping it, all the way to deploying a model and figuring out what it's actually telling us.
Exactly. We'll hit the critical steps, the essential Python tools you need, and yeah, those common pitfalls to watch out for.
Okay, great. So let's start by setting the stage. When we talk about structured data and machine learning, what are we really defining there?
At its core, structured data is just organized in a table. Like you said, a spreadsheet, a database table. Each row is a single sample or observation. Think one customer, maybe one house.
Right.
And each column is a feature of that sample, like the
Right.
customer's age or the house's square footage.
So for houses, each row is one house. Columns are bedroom, size,
Yeah.
location, that kind of thing.
Precisely. And in ML, we use standard notation for this. X usually represents the input matrix. It's all your features.
Okay.
And Y is your target vector. That contains the labels or the values you're trying to predict.
Got it. So predicting house prices, Y is the price. And the big goal is finding some function, let's call it F, where Y is basically F applied to X. We're trying to map inputs to outputs.
That's the essence of supervised learning, yeah.
Yeah.
And to get there, the industry has this widely recognized roadmap, CRISP-DM, the cross-industry standard process for data mining.
Crisp DM. Okay. Sounds a bit formal. But it's actually a very logical cycle, isn't it?
It really is. It kicks off with business understanding. You absolutely need to know why you're building the model, what problem you're solving.
Right.
Then data understanding, really digging in, exploring the raw data. Next is data preparation, and honestly, this often takes up the most time.
I've heard that.
Yeah. Then modeling, choosing, and training your algorithms. Evaluation comes next, checking how well the model performs against your goals. And finally, deployment, putting it into action. But importantly, it's a loop. You often circle back to earlier stages to improve things.
It's never really finished, just constantly refined. Okay. Now, for the practical side, the author really emphasizes Python. It's definitely dominant for this kind of work. What are the key libraries we'll lean on here?
Python's the go-to, yeah, for good reason. For data wrangling, especially structured data, Pandas is indispensable. It makes working with those table-like structures, data frames, really efficient. Then for the actual predictive modeling, scikit-learn is the absolute workhorse. It gives you a consistent way to use a huge collection of algorithms, makes building models much more streamlined.
Okay, so pandas for data shape, scikit-learn for the models. But what about seeing what's going on? How do we build intuition visually?
Good point. That's where Yellowbrick shines. It's a great visualization library built specifically for model evaluation. Yeah. It makes complex metrics way easier to grasp.
Oh.
And inevitably, you'll deal with missing data. Missing Dino is excellent for exploring those patterns visually. It really helps understand where things are missing.
A solid toolkit then.
Yeah.
Now, I remember the author mentioning JIT installation. What's the practical idea behind that? Why not just install everything up front?
JIT, just in time. The big advantage is avoiding what we call dependency hell.
Right.
Instead of installing every single library right away and, risking version conflicts between them, you just install what you need when you need it for a specific task. It keeps your project environments much cleaner, much more manageable, fewer headaches later.
That makes a ton of sense. Avoid the clashes. And for managing those installs, it's typically pip or conda, right? And the importance of virtual environments.
Exactly. Pip is Python's standard package installer. Conda comes with Anaconda, which is super popular in data science. Both let you create these isolated virtual environments for each project. Absolutely crucial. Different projects might need different library versions, and environments stop them from interfering with each other. Plus, you can generate a requirements.txt or environment.aml file so others can easily recreate your exact setup.
Okay, tools ready, roadmap clear. Let's dive into a classic example that really illustrates these steps.
Mm,
Predicting survival on the Titanic. It's such a great teaching tool for classification
it
problems.
really is perfect for that. The
Yeah.
goal is simple. Predict if a passenger survived, which we usually code as 1, or died, coded as 03.
Mhm.
We do that based on their features, things like passenger class, sex, age, number of siblings or spouses aboard, SIBs, fare paid, where they embarked. It's a binary classification task.
And this immediately brings us to what many say is the hardest, most time-consuming part, data cleaning. Sounds boring, but it's absolutely critical.
Oh, completely. You usually start with an initial inspection, use df.d types in pandas to see what data types you have in each column, integers in 64, decimals, float 64, or object, which often means strings or mixed types that you'll need to deal with. Because most machine learning algorithms, especially in scikit-learn, need purely numerical input, and they usually can't handle missing values either.
Ah, the missing data mystery. Why are missing values such a big deal for most algorithms?
Well, simply put, most algorithms just crash or throw errors if they hit a missing value. Now, some newer ones like XGBoost, CatBoost, like GBM, can handle them internally, which is neat.
Okay.
But for many standard algorithms, you have to explicitly address the missing data first. You
Mhm.
can check for it using df.isnull.sum to get counts, or df.isnull.100 for percentages.
And misAnull helps you see those patterns, right? Like in a matrix or bar chart.
Exactly. It helps you spot if the missingness is random or if there are patterns, like maybe age is often missing when cabin is also missing. That can give you clues.
Interesting. So how do you handle it? What are the strategies?
You've got a few main options. The sort of last resort is often dropping data. You might drop rows with missing values using drop no, or entire columns using drop. If, say, a column is mostly empty, like the cabin column in Titanic is often mostly nulls.
But dropping feels drastic. What if you lose too much information?
Good point. That's where imputation comes in, basically, filling in the blanks. For a numeric column like age, you might fill missing values with the median or mean age of the other passengers.
Okay.
But here's the critical part. You must only calculate that median or mean, or whatever imputation strategy you use, on your training data. Then you apply that same learned value or imputer to fill missing values in your test data.
Ah, to avoid data leakage.
Exactly. You can't let information from the test set leak into your training process. That's cheating. For more complex cases, scikit-learn has things like iterative imputer, which uses other features to predict and fill in missing values. It can be more accurate than just using the mean.
So you learn the filling rule from the training data, apply it to the test data. Got it. I also recall the author suggesting adding an indicator column.
Yeah, that's another clever strategy. You create a new binary column, maybe cabin missing. That's 1 if the original cabin value is missing, and 0 otherwise. Sometimes the fact that data was missing is itself predictive information for the model.
Interesting. So you preserve that signal, but while you're carefully cleaning, you also need to watch out for something sneakier. Leaky features.
Oh, yes. Leaky features. These are dangerous. The author points out body and boat in the Titanic dataset as classic examples.
What makes them leaky?
They contain information about the outcome survival that simply wouldn't be available at the time you'd make a real prediction. The body number was assigned only if someone died. The boat number only if they survived and got on a lifeboat.
Ah, so if the model sees those, it's basically cheating. It already knows the answer.
Precisely. It leads to inflated performance scores during development that completely vanish in the real world. You have to identify and remove these leaky features.
Makes perfect sense. If you're predicting survival, a column saying survived on boat X is a dead giveaway you won't have later.
It's exactly right. Okay, so once the data is clean, next up is feature engineering and pre-processing. This is where you transform the data to make it work better with the models.
Right, like turning text categories into numbers, using dummy variables, or one-hot encoding, turning male and female into numerical columns.
Yes, exactly. Pandas has a function called getDummies that's perfect for this. It creates new columns like sex male and sex female with zeros and ones.
But then you run into multiclinearity, right? If you have both sex male and sex female, they tell you the exact same thing, just inversely.
Good point. Yeah, they're perfectly correlated. If sex female is 1, sex male must be 0. For some models, keeping both can make interpreting feature importance a bit tricky. So it's common practice to drop one of the dummy columns created for each original category. Knowing sex female is 0 tells you sex male must be 1.
Okay, that makes sense. And are there other ways to encode categories, especially if you have tons of them? You mentioned high cardinality data.
Correct. If a column has lots of unique categories, think something like zip codes, maybe one hot encoding creates way too many new columns. This is high cardinality. In these cases, alternatives like label encoding, assigning a unique number to each category, or frequency encoding, replacing categories with how often they appear, can be useful. Label encoder is simple, but implies an order which might not be real.
Okay. And then there's normalization or standardization. Why is scaling features so important for certain models?
Yeah, this is key for many algorithms, especially those based on distance, like support vector machines, SVMs, or k-nearest neighbors, KNN. They can be sensitive to the scale of features.
How so?
Well, if one feature, like fair, has values ranging from 0 to 500, and another, like age, ranges from 0 to 80, the fair feature might numerically dominate the distance calculations purely because its numbers are bigger, even if age is actually more important for prediction. Standardizing scales features to have a mean of 0 and a standard deviation of 1, putting them on a level playing field.
Got it. Prevents big numbers from having undue influence just by virtue of being big. Okay. And then, before we actually start training, the golden rule. The train to split. Why is this absolutely fundamental?
Always split your data. You use model selection.train to split from scikit-learn. This is non-negotiable if you want to realistically assess how your model will perform on new, unseen data.
Okay.
If you only test on the data you trained on, you have no idea if the model just memorized the training examples. It might fail completely on data it hasn't seen before. It's about checking generalization.
Right, the ultimate goal. Okay. Data, meticulously cleaned, prepped, split. But before modeling, you also stress the value of exploratory data analysis, ED. Why take time for this?
ED is crucial for building intuition. It's about really understanding the distributions, the relationships, the weird quirks in your data. You use summary stats with describes, visualize distributions with histograms, fair maybe, see relationships with scatter plots, age versus fair. Libraries like Yellowbrick or Seaborn make this easy. And it's also the perfect time to talk to domain experts. They can provide context or spot things in the data that you might miss.
I find those Seaborn plots like pair grids or box plots and violin plots really helpful, seeing how feature distributions differ for survivors versus non-survivors, for example.
Exactly. And correlation heat maps are great for spotting features that are highly related to each other. For more complex, multivariate views, you have things like RADVIZ or parallel coordinates from Yellowbrick or Pandas. They try to visualize if your target classes are separable in higher dimensions. It's all about getting familiar with the landscape before you build on it.
Okay, landscape surveyed. Now, model selection, training, evaluation. And the first big idea is the no free lunch theorem. Sounds philosophical.
It kind of is. But it's a core machine learning truth. It basically means no single algorithm is universally the best for all problems or all data sets.
No silver bullet.
No silver bullet. What works brilliantly on image data might be terrible for predicting customer churn from tabular data. The skill is matching the right algorithm or family of algorithms to your specific data and your specific problem. You need to experiment.
Right. And before trying anything complex, you always need a baseline model. Why start simple?
Because you need a benchmark, something to compare against. A very simple baseline is the dummy classifier in scikit-learn. It might just always predict the most frequent class.
Like if 70% survived Titanic, it just predicts survived for everyone.
Exactly. Or it might predict randomly based on the class distribution.
Yeah.
If your fancy, complex model can't significantly beat that simple baseline, then it's not actually providing much value.
Right.
It highlights why metrics like accuracy alone can be so misleading, especially with eValence data.
Like the fraud detection example. If only 0.1% of transactions are fraud, predicting no fraud every time gets you 99.9% accuracy, but it's useless.
Precisely. So, okay, assuming we want to beat the baseline, what are some common classifiers we should
Yeah, what's in the typical toolkit?
Well, you have logistic regression. Despite regression in the name, it's a classification algorithm. Great for estimating probabilities, often quite interpretable. Then there's naive Bayes, which works surprisingly well, especially for text, even though it makes a strong naive assumption that features are independent.
Okay.
Support vector machines or SVMs. These try to find the optimal boundary or hyperplane to separate the classes. They can handle nonlinear relationships using something called the kernel trick.
Right. And k-nearest neighbors, KNN?
KNN is different. It's instance-based. It doesn't really learn a model in the traditional sense. It just memorizes all the training data points. To classify a new point, it looks at its K nearest neighbors in the feature space and takes a majority vote. Simple concept, but can be effective. Scaling data is super important for KNN.
Because it's distance-based. Makes sense.
Right.
What about tree models?
Decision trees are very interpretable. They create a set of if-then-else rules, easy to understand, but they can easily overfit the training data, learn it too specifically. That's where random forests come in. They are an ensemble method. They build many decision trees on different random subsets of the data and features, and then average their predictions, or take a majority vote. This bagging approach drastically reduces overfitting and usually improves performance and robustness.
Ensemble power. And then the really popular ones for structured data these days, XGBoost and LightGBM.
Ah, yes. Gradient-boosted trees. These are also ensembles, but they build trees sequentially. Each new tree tries to correct the errors made by the previous ones. They're often state-of-the-art for structured, tabular data. Very powerful, very efficient.
And you can even combine models with stacking.
Yeah, that's a more advanced ensemble technique. You train several different models, and then you train a final meta model that learns how to best combine the predictions from the first set of models. Can sometimes squeeze out extra performance.
Okay, so we have a family of algorithms, but how do we tune them for our specific data? That's where hyperparameters come in, right?
Exactly. Hyperparameters are the knobs and dials of the algorithm that you set before training starts. They control the learning process itself, like the K in KNN or the depth of a decision tree.
So how do you find the best settings?
The standard approach is Grid Search CV from Scikit-learn. You define a grid of hyperparameter values you want to try, and Grid Search CV systematically trains and evaluates the model using cross-validation for every single combination on that grid. It then tells you which combination performed best according to your chosen metric.
A systematic search. Got it. Now, evaluation, we know accuracy isn't enough, especially with imbalanced classes. How do we get a better picture?
The confusion matrix is your starting point. It's
Yeah.
essential. It breaks down predictions into 4 categories: true positive, TP, true negatives, TN, false positives, FP, and false negatives, FN.
TP, correctly predicted positive. TN, correctly predicted negative. FP, wrongly predicted positive.
Pregnant man error. Right. Type 1 error.
Right, and FN, wrongly predicted negative.
The pregnant woman told she isn't error. Type 2 error. Those analogies really help. A good confusion matrix has high numbers along the main diagonal, PP and TN.
So from the matrix, we get better metrics, like recall.
Exactly. Recall, also called sensitivity, or true positive rate. It answers, of all the actual positive cases, what percentage did we correctly identify? High recall means you're finding most of the positive cases.
And precision?
Precision answers. Of all the cases we predicted as positive, what percentage were actually positive? High precision means that when your model says something is positive, it's usually right.
So there's often a trade-off between recall and precision.
Often, yes. Improving one can sometimes hurt the other. That's why the F1 score is useful. It's the harmonic mean of precision and recall, giving you a single number that balances both. Especially good for imbalanced classes.
And then there's ROC-AUC, area under the curve. What's that telling us?
The ROC curve plots the true positive rate, recall, against the false positive rate as you change the probability threshold for classifying positive. A model that's better at distinguishing between classes will have a curve that bows further towards the top left corner.
So a higher area under that curve, AUC, is better?
Generally, yes. An AUC of 0.5 is random guessing, and 1.0 is perfect classification. It gives a single score summarizing the model's ability to discriminate across all thresholds.
And we can visualize these. Yellow brick helps here.
Yes, Yellowbrick can plot the ROC curve directly. It can also plot the precision recall curve, which, as we said, is often more informative than ROC when you have highly imbalanced data.
What about the cumulative gains plot? That sounded very practical.
It is. It helps answer business questions. It basically asks, if we target the top X% of individuals ranked by our model's predicted probability, what percentage of the total actual positive cases will we capture?
Like your Titanic example. Targeting the top 65% highest probability passengers might capture 90% of all the actual survivors.
It's exactly. Very useful for resource allocation. Related to this is the lift curve. It tells you how much better your model is than random targeting. A lift of 2 means targeting based on your model is twice as effective as picking randomly.
Great for showing value. And the learning curve tells you about data needs.
Yes. It plots model performance, like accuracy or F1, against the amount of training data used. If both the training score and validation score have plateaued but are far apart, you might have high variance, overfitting. If they've plateaued close together but at a low score, you might have high bias, underfitting, and need a more complex model. If the validation score is still increasing with more data, then gathering more data might actually help.
Super useful for deciding next steps. And finally, the discrimination threshold plot.
Also from Yellowbrick. This one directly visualizes the trade-off we talked about. As you move the probability threshold, like default is 0.5, it shows how precision, recall, F1, and crucially the Q rate, the percentage of cases flagged as positive change. Essential for operational decisions, like how many fraud alerts you can afford to investigate.
Understanding those practical trade-offs is key. Okay, model built, evaluated, tuned. Then you deploy it. Saving it with Pickle and maybe putting it in a web service.
That's the typical path, yeah.
Yeah.
You serialize your trained model object, often using Pickle or JobLib, and then build an application, maybe using Flask or FastAPI, or use a cloud platform like AWS SageMaker, Google AI platform, to serve predictions based on new incoming data requests.
All right. We've built, trained, evaluated. But complex models like random forests or especially deep learning can feel like black boxes. Understanding why they make predictions model interpretability seems increasingly important.
It absolutely is. For compliance, for debugging, for building trust, for actually learning from the model, you need to understand how it's working.
So how do we peek inside? For tree models, you mentioned feature importance.
Right. Models like decision trees, random forests, XGBoost, LightGPM can usually give you a score for each feature, indicating how much it contributed on average to reducing impurity or making correct predictions across all the trees in the model.
So for Titanic, it might say sex was the most important feature overall, then maybe P class, then A.
Exactly. It gives you a global sense of what the model found important. But what about explaining a single prediction? Or interpreting a model that doesn't give feature importance as easily, like an SVM or a neural network?
Yeah, how do you handle those truly opaque ones?
That's where techniques like LIME come in. LIME stands for Local Interpretable Model Agnostic Explanations. Keyword, local. It explains why the model made a specific prediction for one particular instance.
Okay, how does it do that for a black box?
It's clever. For the instance you want to explain, it creates a bunch of slightly perturbed versions of that instant changing future values a little bit randomly. It gets the black box model's predictions for all these perturbed neighbors. Then, if it's a simple interpretable model like a linear regression, locally to just that instance and its perturbed neighbors, weighting neighbors by proximity. This simple local model approximates the complex model's behavior just around that one point.
Fascinating. So it builds a simple explanation that's locally faithful. For a specific Titanic passenger, Lime could highlight that being female, and in first class, strongly push the prediction towards survived for that individual.
Precisely. It gives you instance-level reasoning.
What about understanding feature effects more globally across the whole data set?
For that, we have partial dependence plots, PDPs. PDPs show the marginal effect of one or two features on the predicted outcome of a machine learning model while averaging out the effects of all other features.
So you could see, on average, how does increasing age affect the predicted probability of survival?
Exactly. Or you could do a 2D PDP to see how age and fare interact to influence the prediction, on average.
And if the model is really a black box, you mentioned training a surrogate model?
Yes, that's another approach. If your main model is, say, a complex neural network that's hard to interpret directly, you can train a simpler, inherently interpretable model, like a decision tree, not on the original data, but on the predictions made by your complex model on that data. Then you interpret the simpler surrogate model to get an approximation of how the complex one behaves.
A proxy interpreter.
Okay.
But the real game changer you highlighted is SHAP, Shapely Additive Explanations. Why is it so powerful?
SAP is fantastic. It's built on solid game theory concepts, Shapley values. It's model agnostic like Lime, but it provides both global consistency and local accuracy. SAP